Neutron stars are among the most extreme and explosive objects in the universe. Despite having atomic nuclei just a few kilometers across, they possess a mass comparable to that of a star and incredibly high density. This is attributed to their formation through gravitational collapse following a supernova explosion. Music stars exist in a fragile equilibrium. Trillions upon trillions of tons of hot plasma are compressed inward by immense gravity. Under this intense pressure, electrons merge with protons to form neutrons. Hydrogen fuses into helium nuclear fusion. The energy released by fusion attempts to overcome gravity and escape. This balance sustains a stable state until the hydrogen is exhausted. Medium mass stars, such as the Sun, currently reside in this equilibrium phase. They fuse helium into carbon and oxygen before eventually becoming white dwarfs. But for stars far more massive than the Sun, the scenario becomes far more dramatic when their helium supply is exhausted. In a brief interplay between gravitational pull and centrifugal force, gravity prevails, causing the star to contract more intensely than before. Its core grows hotter and spins faster, while the outer layers swell hundreds of times larger due to centrifugal force. Fusion reactions forge increasingly heavier elements. Over centuries, carbon fuses into helium. Within a year, helium fuses into oxygen. Within months, oxygen fuses into silicon, and silicon transforms into iron in a single day. Then, silence. Iron is the endpoint of nuclear fusion. No further fusion occurs, and thus no energy is released. Fusion abruptly halts and equilibrium reaches its limit. Deprived of fusion energy's radiation, the core rapidly collapses under the immense weight of its outer layers. Events spiral toward extreme and spectacular change, which inherently repel each other with great force. The pressure within the collapsing star becomes immense. Electrons and protons fuse into neutrons, then compress together like an atomic nucleus. An iron ball the size of Earth is squeezed into an atomic nucleus cluster the size of a city. Not only the core, the entire planet plunges inward at 25% the speed of light, drawn by its own gravity. The core's collapse generates an outward shockwave, ejecting the remainder into space. This is the supernova explosion we know, which will illuminate the entire galaxy. What remains is the so-called neutron star with a mass roughly 1,000,000 times that of Earth compressed into a sphere about 25 kilometers across. So dense is this mass that all humanity could fit within a single cubic centimeter, illuminating the entire galaxy. What remains is the so-called neutron star, possessing a mass roughly 1,000,000 times that of Earth, yet compressed into a diameter of about 25 kilometers. So dense is it that all humanity combined would weigh the same as 1 cubic centimeter of neutron star material. This equates to placing approximately 1 billion tons of mass into a space the size of a sugar cube, like fitting Mount Everest into a coffee cup. From an external perspective, neutron stars are among the most powerful celestial bodies, possessing gravitational forces second only to black holes. Should they be any denser, they would form black holes. Light bends around them, meaning we can simultaneously see both the front and part of the back. Surface temperatures can reach 1,000,000 degrees Celsius, compared to the Sun's mere 6,000 degrees Celsius. Additionally, let's examine the neutron star's interior. Though these massive neutron stars are a type of star, in some ways they resemble planets. For instance, they have a hard outer shell